Internal combustion engines can be operated on different types of fuels such as liquid fuels, gaseous fuels, solid fuels. The design of the engine usually depends upon the type of the fuel used. Solid fuels. This type of fuel was used in early engines. During the initial stages of engine development, solid fuels such as finely powdered coal was used. However, due to the problem of handling the fuel as well as in the disposing of the solid residue or the ash after combustion, solid fuels find little practical application today. Further, there are storage and feeding problems associated with the solid fuels as compared to the gases and liquid fuels. However, the attempts are being made to produce gaseous or liquid fuels from charcoal for their use in engines. Gaseous fuels. Gaseous fuels are ideal for internal combustion engines. They mix more homogeneously with air. However, their use is restricted in automobiles due to their storage and handling problems. Gaseous fuels are suitable for storage power plants near the source of availability of fuel. They can be liquefied under pressure to reduce storage volume, but this process is very expensive and risky. Liquid fuels. The liquid fuels are most widely used in modern internal combustion engines. Basically, they are derivatives of liquid petroleum. The commercial types are benzyl, alcohol, petroleum products. Petroleum. Petroleum, generally obtained from crude oil, is a mixture of many hydrocarbons with varying molecular structure. It contains small amounts of sulfur, oxygen, nitrogen, and impurities such as water, sand, etc. The linking of hydrogen and carbon atoms in different ways in a hydrocarbon molecule influences the physical and chemical properties of different hydrogen groups. The carbon and hydrogen combine in different proportions and molecular structures to form a variety of hydrocarbons. Depending on the number of carbon and hydrogen atoms, the petroleum products are classified into various groups. Paraffin series is shown here. Olefin series. Unsaturated as they contain one or more double bonds between carbon atoms. Naphthalene series. Have a ring structure, saturated and stable. Aromatic series. Aromatics generally make good gasoline fuel. They have high densities in the liquid state and thus have high energy constant per unit volume. Aromatics will dissolve a greater amount of water than some other hydrocarbons. This can create fuel line freezing problems when temperature is lowered and some of the water comes out of the solution. Aromatics make poor CI engine fuel. Anti-knock quality. Anti-knock quality improves the increasing number of carbon atoms and the compactness of molecular structures. Normal paraffins exhibit the poorest anti-knock quality when used in SI engine. The aromatics offer the best resistance to knocking in SI engines. For CI engines, normal paraffins are the best fuels. As the number of atoms in the molecular structure increases, boiling temperature increases. Hence, the fuel with lesser atoms in a molecule are more volatile. The high heating value with increased number of hydrogen atoms in a molecule. Therefore, paraffins have the highest heating value and the aromatics the least. With no self-ignition, the pressure force on the piston follows a smooth curve, resulting in a smooth engine operation. When self-ignition occurs, pressure forces on the piston are not smooth and the engine knock occurs. Let us see what is rating of fuels. Fuels are rated for their anti-knock qualities. Gasoline is rated for octane number and diesel is rated for C10 number. Resistance to knock depends upon the chemical composition of fuel or characteristics of hydrocarbon in the fuel, fuel-air ratio, ignition timing, engine speed, shape of the combustion chamber, compression ratio, and etc. Rating of fuels for SI engines. Anti-knock property is compared with reference to isooctane, that is 100 octane number, which is a very good anti-knock fuel, and heptane, whose octane number is almost 0, that is very poor anti-knock fuel. Fuel with octane number 70 indicates 70% octane and 30% heptane. Let us see what is the definition of octane number. It indicates the percentage by volume of isooctane in a mixture of isooctane and heptane, which exhibit the same characteristics of the fuel in a standard engine under a set of operating conditions. Common octane numbers are 87 to 95 and higher values for racing cars. Test for rating octane number. Two most common methods of rating gasoline and other SI engine fuels are motor method and research method. These give the motor octane number MON and research octane number RON. Another less common method is aviation method used for the aircraft fuel, and this gives an aviation number or aviation octane number AON. The engine used to measure MON and RON was developed in 1930s. It is a single cylinder overhead valve engine that operates on 4-stroke Otto cycle with variable compression ratio from 3 to 30. Test conditions to measure MON and RON are shown below. Test procedure. The test engine is run at specific conditions using the fuel being tested. Combustion ratio is varied until a standard level of knock is experienced. The test fuel is then replaced with a mixture of two standard fuels. The intake system of engine is designed as such that the blend of two standard fuels can be varied to any percentage from all isohectane to all N-heptane. The blend of fuel is varied until the same knock characteristics are observed as with the test fuel. The percent of isooctane in the fuel blend is the octane number given to the test fuel. Octane number. There are a number of gasoline additives that are used to raise the octane number. For many years, the standard additive was tetraethyl lead. A few milliliters of tetraethyl lead in several liters of gasoline could raise the octane number several points. The above figure shows how the compression ratios of automobile engines can be increased with the introduction of TEL in the 1920s. Gasoline additives. Rating of fuels for CI engines. Ignition delay is the prime factor for auto ignition or knock. Ignition delay is the time between start of injection and initiation of combustion. Long ignition delay, that is a rapid pressure rise, occurs which causes knock. Short ignition delay, incomplete mixing happens or more smoke is produced. Ignition quality is checked by C10 number. Anti-knock property is compared with reference to C10, that is which causes 100 C10 number, or which is a very good anti-knock fuel. Alpha methyl naphthalene, which has 0 C10 number and is a very poor anti-knock fuel. Fuel with octane number 60 indicates 60% C10 and 40% alpha methyl naphthalene. C10 number. It indicates the percentage by volume of normal C10 in a mixture of C10 and alpha methyl naphthalene, which exhibits the same ignition characteristics or ignition delay as the test fuel when combustion is carried out under specific operating conditions. C10 number is a measure of ability to auto-ignite quickly when the fuel is injected into combustion chamber. Higher the C10 number, lesser the tendency to knock. Further, too high a C10 number may induce pre-ignition. Diesel usually has a C10 number between 40 to 60, whereas gasoline has a C10 number of 10 to 20. That is why it is not suitable as a fuel for CI engine due to its pure auto-ignition quality. It should have a good anti-knock quality, must have short ignition delay, must be sufficiently volatile in the operating range to ensure proper mixing and complete combustion, should not promote smoke in the exhaust, should not cause corrosion or wear in the engine components, easy handling and availability. Diesel fuel specifications. Fuel number 1D is used for cold weather applications, and number 2D is the most common fuel for diesel vehicles, and number 4D is used for medium to low speed engines used for stationary applications. Diesel fuels can also be improved by addition of fuel additives, and fuel additives are shown here.